you know, so I'll see if I don't fall asleep in the middle of doing it. I'll try to have that graded back to you tomorrow. All right? So begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, I thank you for this class, for these students. Just ask you to just bless our work today. Help us to understand a little bit more about your creation, about arclength, about how to understand the geometry of curves, Lord, with calculus. In your name I pray, Lord Jesus. Amen. So I guess first off, I need to just introduce some language, right? And there you go. So first of all, notation-wise, I've been using for the parameterization of a path. And so the notation, when I use R, I use this notation for a lot of different things in here, right? Sometimes I use it for the position of a path. If I have R of uv, I'm talking about the parameterization of a surface, right? So I generically think of this as like a position vector in space, which I may add more context to, all right? But for today, and usually, it's not, you can use different letters, but this is the one I'm going to use. If we have C, which is a subset of Rn, right, then an oriented curve, let this be, my bad, I'm missing a word here, let C, subset of Rn, be an oriented curve. What's an oriented curve? All right, an oriented curve which starts at P and ends at Q. I'll say from P to Q. All right? We say gamma, and I think I put a vector on this thing. Yeah, gamma vector, which is a function from the unit interval from A to B to C, is a parameterization right? A parameterization. Oh, I lost some details here, right? Smooth and nonstop. All right, smooth nonstop parameterization, I should say. If what? Of C. If what? What is my conditions here? If gamma is smooth, what's that mean? I'll put some quotes around that. All that means is that the derivatives exist for the function. You can differentiate it, and those derivatives exist. And remember how we defined the derivative of a space curve? Like you differentiate component-wise, right? So that means the first, the second, all the way out to the nth component functions, they all can be differentiated as many times as you like, all right? And gamma prime of t is not equal to 0 for all t in the interval from A to B, right? I think you guys probably know, but in case you don't, this is equivalent to saying what? This just means A less than or equal to t less than or equal to b, right? Okay? What is this? So smooth means you can differentiate it as many times as you want. This right here is the, where the rubber hits the road for this criteria, right? Non-stop. Non-stop means what? It doesn't stop, right? What would it take for the path, the parameterization here to stop? Well, if the derivative was 0, it stopped, right? If we let the derivative be 0 for the parameterization of a curve, it will throw a monkey wrench into all of our plans. This cannot be. We cannot allow this. All right, so nonstop, we want nonstop parameterization. And the other thing, of course, we want gamma of A equals to P, and we want gamma of B equals to Q. And I'm going to put vectors on these typically, all right? But listen, this is just another notation which I try to hang my hat on, like I try to use gamma for the parameterization of a curve. I don't think I ever use gamma for the parameterization of a surface, right? The R vector I use for both, notation-wise. Now here's a picture of what's going on. So we've got, here's P, all right? Here's Q. And, you know, there's some path that goes from one to the other. Now, oriented curve means that it has a sense of direction, right? There's a direction in which the curve is going. That's oriented. So if we parameterize the curve, it should go in the same sense, right? Like P is gamma of A, Q is gamma of B. So we have that. So the first thing you'd want to talk about in terms of the geometry of this curve is the arc length of the curve, all right? So let me just kind of draw a little picture for that. All right. This always goes badly, but I will attempt it. So if I'm, say, looking from, say, here to here, I can think about like the shadow of that. Oh man, I can never draw this curve. I can never draw this picture worth anything on the fly. Give me a second. I got to think about it. All right, so this is the x direction. This is like the y direction. Man. I'm unsatisfied with the scale of my drawing. Oops. I've just misted the air with the board cleaner. That doesn't really accomplish anything. Well, it does accomplish something. If you walk into that cloud and like inhale it, it's a bad day. It's not good. Let's try this again. So, big curve, okay? But this is just zoomed in. And what I want to think about is, from this point, maybe from this point to that point. I will get it eventually, guys. I'm just having trouble in my mind's eye seeing it. You know, I'm a dummy. I do have these notes for a reason, right? Here's a picture. Let me try to recreate the magic there. So, so I have better success if I make the curve bend the other way in my picture? Oh no. All right. So sorry, guys. This should not be hard. All right, so here's my curve. I want to look at the shadow of it down here. Maybe. No, I don't want to do that either. I'm sorry, I get really annoyed when I can't draw something, you might have noticed. Here's a horrible picture. That's still not right. You guys are laughing at me. You're horrible people. Yeah, like we're just laughing because we also can't draw these pictures. Like, just joking. All right, so I will eventually get it. I didn't realize I should have planned how to draw this before class. It like hadn't occurred to me. Remember how to draw this. Duh. All right, so look, the point is I'm trying to make this like in the x direction. I'm trying to make that in the x direction. I'm trying to, and so we're gonna be able to argue that what this really should be essentially is dx dt times dt. That's, well, let me not even write it that way. Let me just be a little bit more. dx. This should be the dx. This is the little bit of dx in the x direction. This should be the little y direction, and then the z, if I can find my marker, should be the vertical piece, all right? Up to the limits of my artistry, which is apparently not much. And so, you know, if you could imagine the shadow of this curved thing is back here, but these are right angles, right? And so of course, you can think about the direct line segment that connects the end point to the starting point, right? Something like this, right? And that purple would be exactly what? It would be exactly dx squared plus dy squared plus dz squared, right? By our three-dimensional distance discussion, that would be the length of the line segment which connects the initial point to the final point. Do we agree? Like from here to here? That would just be the length of the purple dotted line segment in 3 dimensions, right? Now here I'm using dx, dy, dz because I'm thinking of them as being very, very small. If you like, you could replace this with delta x, delta y, delta z to think about a finite increment, right? But these would be a good approximation, but this is not an approximation, actually. This is exact, ds squared, where ds is going to be the length of the curve, right? So if we were actually taking a finite extent, this would be an approximation, right? But in the limit that we let the delta x, delta y, and delta z be 0, that gives us the actual arc length subtended, right? So that is why the arc length is that. Now that doesn't, I mean, how do you calculate that? How do you add up the arc lengths? Well, that's better done by applying the mean. What we do, technically speaking, is you apply the mean value theorem on the increment you're looking at. The mean value theorem says that the change in x can be represented by the derivative of x at some point in that interval times the change of the change in time, right? But what that ultimately means is basically you can divide and multiply by dt, formally speaking. So like a formula for this, right, is just dx dt squared plus dy dt squared plus dz dt squared all times dt squared, right? Now that's just formal nonsense I'm writing on the board, but if you want the careful mathematics of that, we're applying the mean value theorem to the polygonal approximation of the curve, right? You're basically replacing the curve with its its broken line segment approximation. You apply the mean value theorem on each one of the line segments to respectively the x, y, z components of the path. When you do that, you find a derivative, and then you can, well, ultimately what you get is this, right? The arc length for the curve is equal to the integral from a to b of the square root of dx dt squared plus dy dt squared plus dz dt squared. Now, of course, I made my definition for the path up here in Rn, but I'm giving you the arc length formula in 3 dimensions, right? You guys should have already studied the 2-dimensional one in Calc 2, right? Or maybe Calc 1, depending where you went. Yeah? Does this make sense? I could spend 20 minutes actually going through all of the careful, picky mean value theorem stuff and like explicitly, but I don't think it really serves you much for me to do that. I think it's better for us to try to understand heuristically why this formula is true. And heuristically why it's true, it's because the infinitesimal arc length is obtained by the square root of the sums of the squares of the infinitesimal displacements in the x, y, and z direction. And then to find the total arc length, you simply add the infinitesimal up across the curve. This is an example of what's called the infinitesimal method, right? A method which is unreasonably successful. And part of the reason it's unreasonably successful is that you can form a calculus where these dx's, dy's, dt's are actually fractions that are not real numbers. They're just really, really small. They're these things called infinitesimal. There's a formalism of calculus which does that rigorously, which I will not teach. Although there are schools which teach that as the standard calculus. There exist such schools. There's no limits in their calculus. It's just all abstract algebra of calculus. It's called non-standard analysis because it's not standard. So, all right, listen. Let me put this up. Oh, sorry, I'll go over there. So a lot of times you want to talk about the arc length function. So I just gave you the arc length of the whole curve, right? arc length function. So if you just have, you know, a curve, and you've got some base point on the curve, let's say gamma of t naught, right? That's your initial point at some initial time, right? And maybe you want to calculate the arc length starting at that point as a function of the parameter. This is the arc length function. So if you want to calculate the arc length, say, of this much, like here, you might call that S gamma of t, right? And the formula for S gamma of t, if it's bothering you that I'm not putting a vector on the subscript, you are free to add the vector. I probably have added the vector in my notes, but if you'll forgive me for that slight, you know. So here we go from t naught to t, right? And let me be a little bit more, efficient in my notation. Can you guys tell me what's an easier, better thing to write under the square root over there? What is that? I heard the magnitude of the derivative, is that right? Yeah, like look, see this right here? This is exactly what? This is actually the magnitude of d gamma dt, right? Or if you like, it's the magnitude of gamma prime of t. That's what this is, including the square root. It's the length of the velocity vector. In physics, we'd call it the speed, right? It's the speed, if you want to think about it in terms of physical language. So to calculate the arc length function as a function of t, all we've got to do is we got to integrate the speed. We got to integrate the magnitude of d gamma. And look, now this is where I get into trouble. Over here, so I'm going to write it down, but it's wrong. You guys tell me why it's wrong. Why can't I write this? I'd love to write it, but I just can't. Why can't I write that?
Because t is a limit?
Yeah, exactly, because t is in the bound. T is already used. T has a fixed but arbitrary meaning. It's the time which we're calculating the arc length for. See, t has a meaning that's described by this point right here. So I can't use it as the dummy variable of integration. So what I have to do is I have to use a different letter here. We can use whatever you want. You could put a Pac-Man both of these places, whatever. Sometimes I put a U. You could do that, right? You could put tau. I sometimes put tau there. Yep.
So we're still taking the root of each of the components with respect to t, though?
Well, we take them with respect to u. If you can differentiate with respect to u, if you can differentiate with respect to t, you can differentiate with respect to u. T is just a variable. It's not. Listen, your question, you will not really understand what I'm saying until I do an example. So let's do that. We'll do an example, and then I will circle back and tell you all the wonderful properties of the arc length function, right? But let's do an example first. My favorite example, that's non-trivial, it's a really nice example, is the helix. So the helix, there's lots of them, but here's the usual one I look at. Gamma of t is, I don't know, let's say 2 cosine t, 2 sine t. We'll put a 3t over here just to be different. So there you go. This is actually a parameterization of a helix. If you want to know where it goes, well, check it out. X squared plus y squared equals to what? 4 cosine squared t plus sine squared t, right? Factor the 4 out. You got yourself a 4, right? So if you were to draw the cylinder of radius, 2, yeah? This helix is winding around that cylinder, right? And it would look something kind of sort of like what? You know, it just winds around the cylinder, up and up and up. And it also goes, this is t equal to 0, right? T equals to 0, you can try it out. Gamma of 0 is 1, 0, 0, right? So let us actually calculate the arc length function for this, all right? So I'm going to show you what I meant by differentiation with respect to u. It's very silly. There's really nothing to it. See, this means that gamma of u is 2 cosine u to sine of u. This is actually a very good question you're asking, because it strikes at the heart of what's most difficult about today's lecture, which is the idea of substitution. So we substitute u for t. Then you guys know what gamma prime of u is, right? Minus 2 sine u, 2 cos u, 3. And then if you calculate the magnitude of this, what you got? We've got ourselves a 4 sine squared plus 4 cosine squared plus 9. That simplifies to what? Just square root of 4 plus 9, which is 13. So the standard parametrization of a helix, it's an interesting path. It's far from a line, right? The velocity is changing everywhere, right? It's always going up and it's always changing direction around the cylinder. And yet, it has constant speed, which is kind of neat. Constant speed curves are especially nice in the story I'm telling. Now, so you see, we could have done this. So the thing is, we could have done this calculation with respect to t. Now, do you have to change to u and differentiate as a practical matter? You don't, right? You could do the differentiation in t where you're more comfortable, and at the end of that, switch the letter to u at the end of that process. That would be probably a safer route for most people, calculationally. Right? You guys understand that? I could have just differentiated in t and then found the magnitude of that, and then at the end switched over to the other variable. I'll try to illustrate that in a future example. Anyway, there you go. Now we can calculate the arc length function. What is it? And so then you should say, well, what do you mean the arc length function? You're talking about the arc length function as if it's a single choice. Is it a single choice? It is not, right? There's an ambiguity in the arc length function. What is the ambiguity? The ambiguity in the arc length function for a given path, right? And when I say path, I'm talking about a curve which is parametrized. So path has implicit within it the idea you've picked a parametrization, all right? Let us agree on that terminology so that we don't have to say parametrization 1,000 times, which is not a fun thing to say, right? So pick a path. You still have to pick a starting point for the arc length function, right? So if I use 0, well, then there's a unique thing, right? S gamma of t, integral from 0 to t of the square root of 13 dt. My bad. What should I put here? After all, yes, du. I think I heard the still small voice. All right, so I think it was one of you. I don't think it was a spirit. Let's see here. So square root of 13, but who am I to say? Could it have been the spirit speaking through you? Let's see here. 0 to t, which would be like t times the square root of 13. So there you go. Now, listen, as a practical matter, we'll often just write, oh, okay, so s is equal to t times the square root of 13, right? If you want to just let s be the arc length. Sometimes we don't want to write s sub gamma of t because it's kind of like, annoying. Especially if you're going to do some kind of algebra with it, right? Any questions so far? So one of the things we can do, once we find the arc length function, is we can take the curve that we're given, rather the path that we're given, and we can do what's called reparameterize it. we can reparameterize the curve with respect to arc length. Okay? So, notation, definition, gamma tilde of S is going to be equal to gamma of S of sub gamma of T. Now, that's a lovely definition, all right? But let me show you how it actually works out for example 1. For example 1, what's the arc length? What's the parameterization by arc length for this helix? Gamma tilde of S is equal to, well, 2 cosine of something, 2 sine of something. Aw, man, poor planning on my part. I'll just make it smaller. 3 of something, close angle bracket. So what should I fill in the blanks? Do you guys know? Yeah. I heard T over 13. Right idea, but if we solve this for T, we get T equals to S over root 13. So you got the right idea, but the wrong letter. Unless you just said S and I heard T, because my brain was messing with me. It's the weirdest thing. I was listening to verses last night in the children's program, and I heard the children say one thing, but they said that they said another. And so, like, I don't know. Like, it's a question. Did they actually say it wrong, or is it just my brain messing with me because I'm tired on Wednesday night? I don't know. But we need an S there. So to find the arc, let me just put it in plain words for you. To find the arc length parameterization of a path, all you do is you calculate. Now that all you do, I'm being facetious because like this calculation, oh, it's lovely for this helix, but for a general path, even a relatively simple one, this is an impassable calculation in terms of elementary functions. All right? But theoretically, there's a path here. So you find the arc length function, and then allegedly, you can solve for T. You can solve for T, and then you just plug that in to your original formula, and that gives you the arc length parameterization for it. All right? So let's study properties of the arc length more before I do more about this example. So this is remember I told you guys that the fundamental theorem of calculus part 1 matters? This is probably the place where it matters the most in the whole calculus sequence. Honestly speaking, this is the most important application, in my opinion, of the fundamental theorem of calculus part 1. Here it is. Let's see it. So our arc length function is a function of time t, right? S gamma of t, what was it? We said integral from 0 to t of the length of d gamma, d, let's say, I'm going to use a tau this time just to be different because the u, I just dislike the u, honestly. So d tau. You can put whatever letter you like there. Differentiate this. How does that work? What is the derivative of the arc length function? We're taking the derivative with respect to t of, oh, I'm so sorry. Look at this hideous marker. This is Carolina blue. It's the most evil of all blues. Ugh. I mean, it is a pleasant color, but what it represents is a sad, sad thing. Anyway, for the record, if there's any kind of tragedy that's happened to the UNC Chapel Hill recently, I'm not speaking of that. I'm speaking of the spirit of the school and its antagonistic posture towards NC State, a more righteous school. where I graduated from. Anyway, so if you differentiate this, how's that go? You're differentiating integral to variable bound. All you do is you take the integrand, right? And you just shove the t into it. That's it, right? So this is literally equal to, by fundamental theorem of calculus part 1, d gamma dt, magnitude. What I'm showing you is that the magnitude of the velocity vector is the infinitesimal rate of change of the arc length function. I'm not defining it, I'm deriving that. All right, but now we know it. So ds dt is equal to the magnitude of d gamma dt, which in the language of physics is the magnitude of the velocity at time t, right? Well, let me drop the of t for a second here, just not clutter things. Are we good? Question, can I solve, so like this is the problem, can I solve s gamma of t, let's see, how can I say this? So s gamma of t equals to like some function g, all right? Like let me just use this as like as a formula, if you will, just in principle. I want to solve for t. How do I do it? I want to do what? I want to do like, basically I want to calculate s gamma inverse of s gamma of t, right, is equal to t. If you want, right? If I could find the inverse function for the arc length function, then that's what I need to do to solve for t, right? We just did it in the example. It was kind of silly, right? S was what? T times the square root of 13. So in this case, you know, s gamma inverse of s is just equal to, well, if s multiplies by 13, s inverse divides by 13. So it's exceedingly silly, the inverse function there, right? How do you know an inverse function exists? So you need the function to be 1 to 1, right? How can you know a function's 1 to 1? One way you could know is if the function was everywhere increasing, right? If the function's everywhere going uphill, it has to be a 1-to-1 function, right? If you think about that. Is the arc length function always increasing? What's the derivative of the arc length function? It's this, right? And this is greater than 0. Why is it not equal to 0? What did we assume at the beginning of this whole discussion?
It's nonstop.
It's nonstop, right? That's why nonstop is important. If nonstop wasn't put into place, we couldn't invert the arc length function, among other things. But we can, all right? So the arc length function is always increasing, which means that in principle we can find its inverse function, which means, at least in theory, we can solve for t, and we can write the arc length parameterization, right? Now, I'm not saying you can actually find a formula for S inverse in general. Let me show you an example where, like, this is all theoretically possible. Let me try to tell you something else that's like this. You guys in Calculus 2, in Calculus 1 and 2, what did you learn about integrals? Which kind of functions can you integrate? So what I'm just talking through, guys, is this theorem right here. Well, eventually we'll get to the theorem. So this theorem right here, I prove what I just asserted in the text right after here. Oh, rats. And I neglected something else, which is that if we, well, this is just the chain rule. I guess I should probably work that out. Oh, I forgot something. All right, we'll get back to that in a second, but let me show you the example first, because what am I, example 2? All right, so here's one. What if we had gamma of t equal to, oh, I don't know, t cos t, t squared, hyperbolic sine of t. So we calculate d gamma dt. That gives us cos t minus t sine t, right? 2t cosh t. Those are the derivatives. Then we calculate the speed. The speed is the magnitude of the velocity. And that gives us the square root of cosine t minus t sine t quantity squared plus 4t squared plus cosh squared t. And I'll set your mind at ease. There is no corner of pre-calculus that you have forgotten which allows you to simplify this. It is what it is. All right, you cannot fix this. And so the arc length function based at, let's see, what you guys, what point do you want to base it at? I didn't tell you the parameter range, did I? Let's start the arc length function at 2 this time. I mean, it doesn't matter. You can start it wherever you want. I usually start it at 0, though, honestly, folks. And here you go. So it's just cosine of tau minus tau sine tau, quantity squared, plus 4 tau squared, plus cosh squared tau, d tau. And that is the arc length function. And that's as far as we can go. So like on a test or a quiz or something, if I say calculate the arc length function, do not attempt the integral, I mean this. I don't even expect you to simplify these. Although, fair warning, there are lots of examples where simplifying that is so important. Think about that helix example that we just did. What if I hadn't used sine squared plus cosine squared equals to 1? What if I had instead decided to stick with the unsimplified sine squared plus cosine squared? Well, that would have made my life much more difficult, everything that followed after that. Right, anyway. So in principle, even though I cannot solve this for t, right? I cannot solve this for t, but that doesn't stop me writing down gamma tilde of s is actually equal to gamma of, let's see here. I think I may have, did I define that wrong? My spider sense is tingling. Yes, gamma tilde of s is, did I put the wrong thing over here? Gamma tilde of s is gamma of, oh yeah, I did wrong. Look at that. I'm so sorry, guys. This is like totally bogus. Totally bogus. I'm so sorry. Let's fix this. Yeah. That was supposed to be s gamma inverse of s. So you need the inverse to the arc length function. That's what we put. And that's what we did here too, right? So like here, s gamma inverse of s was actually equal to s over the square root of 13. All right? And that is, notice that is what we actually did. We plugged in the inverse function to the arc length function. Theoretically, this exists for an arbitrary path, but pragmatically speaking, I can only actually calculate the inverse for like a specific nice set of examples. Yeah? Which one?
Above the square root of 13.
Yeah, that's an s. Yeah. I'll try not to use 5 in examples with arc length. I know. Yes?
So if we get S, my message just go back. We just set it equal to the result of the integral that we get.
To find, that's right. Yeah, if we can't actually do the integral, that's what we have to accept our fate. That's the deal. Now, I have these notes out, so let's just look at the notes together here for a second, guys. Like, how about example 2.23? What's that? So here, this is a two-dimensional example, right? I mean, I'm surely you saw this example in calculus too, right? This is the parameterization of a circle. The velocity of circle is right there. The magnitude of the velocity of that is simply r. So to calculate the arc length for the whole circle, we just integrate from 0 to 2 pi r dt, which gives us 2 pi r. Woohoo! And also, if you wanted to calculate the arc length function based at 0, you just end up with 2rt, right? Which, you know, when you put t equals to 2 pi, what happens? You get the circumference, right? So this is the, here I did the helix with a and b arbitrary. So I did the calculation for you guys with the 2 and 3 there to make it less weird. But the same calculation goes through with 2 and 3 replaced with a and b. And then you get the square root of a squared plus b squared is the speed. And so the arc length is that. All right? And here is the analog of my follow-up to example 1. This is, if I take the arc length for the helix, the AB helix, and I solve this for t, then that's the inverse function to the arc length, right? I plug that in to where t was, and this gives me the so-called reparameterization of the curve with respect to arc length. Now, I haven't introduced the gamma tilde notation at this point, I think. If I have, then my bad. I should really write. To be clear, this is gamma tilde of s in my usual notation. This is the arc length parameterization of the helix, all right? It's also called unit speed parameterization. Do you guys, what do we mean unit speed? Yeah?
The speed remains constant.
That is true, but what is its speed? So the speed of the helix was square root of 13 in my example 1. What was the speed of gamma tilde of s? So like gamma tilde of s, that's supposed to be a tilde. You guys have to help me out. It was what? 2 cosine of s over the square root of 13, right? 2 sine of s over square root of 13, right? And then 3s over the square root of 13. Okay, so you guys calculate the speed of that for me. Well, before I do that, what is the derivative of this? So we differentiate, we have to do the chain rule, right? What's the chain rule do? It brings out, I'm just going to bring it out. We end up with 1 over the square root of 13 times minus 2 sine of s over root 13, 2 cosine s over root 13, and then, well, 3. But we already have calculated the length of this vector. This has length square root of 13. So what's the length of this? One. It's 1. Let me sell you perhaps on a way you can remember this easier. We have the result that the magnitude, right, of the velocity, right, is equal to ds dt, right? I just argued this a second ago. I erased it, but fundamental theorem of calculus part 1 gives this to us. So what happens when you put t equals to s? What happens when we put t equals to s? Then we have d gamma tilde ds equals to ds ds. I just use a special, listen guys, I'm using the tilde to draw your attention that it is a specific and important geometric choice of parameter. There are infinitely many choices of how to parameterize a given curve. But once you pick a base point, the arc length function is uniquely prescribed. So that's not, there's a specific arc length parameterization given a base point, right? And what is it? It's the parameterization which has the magnitude of the velocity set equal to 1. That's why it's called a unit speed parameterization or a unit speed curve. So here up is here next, you know, I want to look at some of these with you guys. So like this one here, look, so like here, man, there's a chance you don't see that, right? You guys remember how arc length goes in the, oh, you're way ahead of me. You know how the arc length goes, calculations go, right? If they're a book problem, what happens? There's always some conspiracy of algebra to make the thing inside the square root become a square, right? Pretty much. Or it's a problem from the trig substitution section, so it's an integral of the square root that you've got tools to deal with, right? You guys remember trig substitution, right? You're like, please, let's go back to that. That was easier than this, right? So like this one, of course, you end up with the square, and then the square root goes away, and so lo and behold, we can calculate. So here I can calculate the arc length function. So this is, see, here I can calculate the arc length function as function t. Can you solve for t? Can you solve for t as a function of s here? I mean, maybe you can, but I don't want to, you know? I said it is possible to solve, but anyway. Oh, I was midway through a thought, which is that we can integrate any function which is continuous. That's the criteria. A continuous function has an area function which is defined, which means that by the fundamental theorem of calculus, it has an antiderivative, right? However, that does not mean that you can find the formula for the antiderivative. In fact, there are precious few functions that are continuous that we can actually explicitly find the formula for the antiderivative. So in terms of pen and paper closed form attack, the set of like functions which we can actually integrate is pretty small, right? And there are algorithms, there are actually algorithms for deciding whether or not a given function is integrable. Famous example would be like e to the t squared. That's a pretty simple formula, but you cannot find an antiderivative in closed form in terms of elementary functions, right? How do people deal with integral of t squared in statistics? What do? They do what? Power series. No, power series is too hard for statisticians. They don't know that.
Computers?
I can say that. There's no statistician at Liberty, so like I can insult them. What's that?
Computers?
Computers. That's kind of true. But we teach how to find the area under an exponential of a variable squared to like Math 115 students, to Math 201 students, statistics with just algebra. How do we do that? The answer is we make a change of variables. So what you do is you take the Gaussian distribution, which is based on like e to the t squared, you make a substitution in terms of something called the z-score. The z-score converts the interesting Gaussian to the so-called standard normal Gaussian, and then you look up in tables the area under the standard normal. And it turns out that there's a one-to-one correspondence between the area under the standard normal and the area under the original curve. And the z-score is a u substitution to make that happen. Now you guys have had calculus, so you could understand that if you work through it, but they just use it, right? So you have to have some kind of like sneaky trick to get around not knowing the formula for the antiderivative. But anyway, I digress slightly. Let's go on. Here's another example that's kind of ugly. This example it looks uglier than it actually is. All right, so let's look at this calculation here together for a minute. If I can find my laser. Oh, there it is. So you've got 1 plus ae to the t plus be to the t plus ce to the t. So here's my position. Notice this, it's in your best interest to factor out e to the t. Because then you've got e to the t times a constant vector. That's easy to differentiate. How do you differentiate function times a constant vector? Well, you just differentiate the function. And it would be better if these notes also had included like the equation right here. dr dt equals to what? E to the t, right? ABC. So what happens when you calculate the magnitude of a number times a vector? The magnitude of a scalar times a vector is just equal to, the magnitude of the scalar times the magnitude of the vector, right? But what is the magnitude of the absolute value of e to the t? Is e to the t negative? Well, no, right? So that is the magnitude of e to the t, and this is the length of the vector ABC. So there you go. And then we calculate the arc length function like so. E to the t minus 1, because when we integrate e to the u, we get e to the t minus 1. This one actually is kind of interesting. We can solve this for t. This is actually the first interesting calculation for like solving for t, right? Subtract 1 to the other side. Subtract 1 to the other side. Oh, wait a minute. No, I'm a dummy. I'm solving for t, right? So the 1's already where it belongs. I take the natural log of this equation. I get that. And then, oh, man. And then you plug that in. I plug that natural log into the t. See, if I put e to the natural log of this, what happens? Yeah, it gives you this, because the e to the natural log of this pops back out that. And then the 1 plus 1 is giving me the a, the plus b, the plus c. Anyway, then you can simplify that, and you get this. At this point, you might recognize what we're looking at. What are we looking at here? It's kind of more explicit in this formalism. Maybe you can see it. This is a fixed point, right? Plus s times this constant vector abc over the square root of a squared plus b squared plus c squared. Well, this is a line. It's a constant vector plus the parameter times a vector. That's the parameterization of a line. See, what this example is about is a really stupid parameterization of a line. And what calculating the arc length parameterization has done is just revealed, oh, it's a line. So there it is. Now, of course, you could have seen it more directly if you just said, well, I'm going to let lambda equal e to the t. If I make the substitution lambda equals e to the t, then r of lambda would be 1, 2, 3 plus lambda times abc. And there, again, it's explicitly obvious that this is a line with base point 1, 2, 3 and direction vector abc. So, oh man, I double scrolled. I'm so sorry. The evil double scroll. Oh man, I double scrolled way into the future. So sorry. All right, so that brings us to section 2.2.2. All right, and let me put this away. I need to draw some pictures for us. This is a discussion we'll start today, but we won't finish today. All right. Actually, now, oh man, I'm a dummy. I was meaning to press the lighting, but I have incidentally obviously pressed the, there we go. I used to have a classroom that every class, the thing automatically came down at like the 20-minute mark. I don't know why, like there was just some bug in like the IT software, and I just like clockwork. I knew a third through my lecture, it was going to come down, go halfway back up, go back down all the way, and then go back up again. Like it just, that was one of the weirder things that these things have automatically done for me. Although by far the most annoying thing that ever happened to me in this regard was I was once teaching in a classroom where I couldn't turn on the lights. See, because the person before me wanted to watch a movie. So they called up IT, they're like, hey dude, we can't turn off the lights. Can you turn off the lights for me? And IT's like, sure man, we'll hook you up. And then, so they turned off the lights in the classroom, right? but they turned them off from like their central hub, and they didn't like reactivate the control in the front. So I get in there, and I got no lights, and I've also got no way to turn on the lights because it's a fourth floor classroom, right? We don't have light switches. So that lecture, I went back to my office and I got a like a lamp, and I put a lamp in front of the whiteboard, and I lectured by lamplight. That was a large lecture section. It was not good. I really should have just been like, you know what? Today's a video. But it was kind of before the time of videos. Anyway, I digress. You guys have any questions about homework before I get into the next spiel? Now's a pretty good time to ask me about homework if you got questions about it. If not, it's cool. I can go on. So nothing coalesced yet? Okay, that's cool. So if we have a curve in 3 dimensions, now some of the things I've told you guys have been n-dimensional. Arc length is just based on the speed of the parameterization. We can calculate the length of a vector in n dimensions just the same as we can in 2 or 3. So arc length is something you could calculate for a path in 26 dimensions. It wouldn't really hurt you much, except, man, you'd have 26 component functions to differentiate. That could kind of get old, right? But what I'm about to tell you is special to 3 dimensions. All right. Perhaps there's a 2-dimensional analog to it, I suppose, but really it's a genuinely 3-dimensional thing. So I've already today spent most of our time talking to you about the arc length function. That's the first geometric thing we can ascribe to a curve. The length along the curve, right? It's very simple. But the next thing we can do is we can ascribe what's called we can assign a vector field along the curve. What's a vector field along a curve? What it is you're attaching a vector at each point on the curve, right? So let me draw a particular vector field here along this curve with this hideous Carolina blue. But this vector field that I'm plotting what do you guys recognize what this vector field is? This would be an example of it's called the tangent vector field. The tangent vector field. And to make things, okay, so if you thought about that, what would be a natural tangent vector field? There are like many of them actually. So a tangent vector field, sort of generically speaking, would just be something that is parallel to the velocity field. Well, what's the velocity field? This could be the velocity field, or this could be a velocity field, velocity vector field. So velocity vector field would just be basically, d gamma dt. That would give you the velocity vector field, right? That would be pointing where? In the direction in which the path is going, yeah? Now, if you have a curve, you can parameterize it 16 different ways from Sunday, right? Like you could take the curve, you can parameterize it one way, right? But you could also double up the parameter, right? You could go twice as fast. You could go like this, or then you could go like this, right? Or you could go like this, and then like this, and then like this. I mean, you can speed up, slow down, as long as you don't stop. There are infinitely many non-stop parameterizations of a given curve. So if we're trying to describe something geometrically, we need to somehow remove the idea of speed from the tangent, right? So while there are many, many different speeds that you could traverse the curve with, the tangential direction, that's geometric, right? So if we want to talk about the tangential direction, we use what's called t. So big T is simply equal to the velocity divided by the magnitude of the velocity. This is the unit tangent vector. And